Hello and welcome to the latest Explaining Science video in which I'll talk about the boundaries of the universe. It's thought that our universe is infinite, or at least very large in extent, but we can only see a small fraction of it. This we call the observable universe. So the observable universe must have some kind of boundary. Logically, we can only see objects lying within this boundary. Let's start with the boundary of the universe. There are actually four different types of boundary to the universe: the particle horizon, the surface of last scattering, the cosmic event horizon, and the Hubble Sphere. When cosmologists talk about the distance between two objects, they normally mean the proper distance. That's the distance which would be measured by an imaginary cosmic-sized ruler joining the two objects together. Obviously, it's not directly measurable. The other thing we need to consider as additional background is the fact our universe is expanding. This means that the distance between objects which are held together by forces such as gravity increases over time, although the objects themselves don't get any bigger, as this simple animation shows. Because of the expansion of the universe, the proper distance between two distant objects always increases with time. In this example, consider photons emitted from a distant galaxy 294 million light years away from Earth. As the galaxy is moving away from us and our Milky Way is moving away from the galaxy, the photons have to travel a bit further, 300 million years it takes them to reach us. When they do, the proper distance of the galaxy is now 306 million light years. Now we come to the definition of the particle horizon. The particle horizon is a theoretical maximum proper distance we can see to. Sometimes it's called the cosmological horizon. So when we look at distant objects, we're looking back on time. So if you look at an object which is at the particle horizon, its light will have been emitted at the very beginning of the universe, and so will have been travelling towards us for the entire age of the universe, 13.8 billion years. The particle horizon is a spherical shell 46.5 billion light years away from the Earth. All the objects we observe today lie inside the particle horizon, which forms the boundary of the observable universe. If an object is further away from us than 46.5 billion light years, it's not observable at the moment. The universe just isn't old enough for its light to have enough time to reach us. At the exact instant of the Big Bang, the particle horizon would have been zero, and as the universe ages, the particle horizon increases. In reality, we can't see all the way back to the particle horizon. The early universe was far too hot for atoms to exist. It contained a plasma of ions and electrons, and radiation can't pass through a plasma. It was only when the universe had cooled enough, roughly 400,000 years old, that individual atoms exist and it was transparent to radiation. The cosmic microwave background is the oldest radiation it's possible to see, and this was emitted when the universe first became transparent to radiation, roughly when it was 400,000 years old. Before this time, as we said before, the universe was opaque, so we can't observe any light emitted before then. The cosmic microwave background radiations comes from a set of points called the surface of last scattering. This forms a spherical shell roughly 46 billion light years away. We can't receive any light from anywhere older than this. One question which often arises is how can we see radiation from the surface of last scattering at a distance of 46 billion light years when the universe is only 13.8 billion years old? The answer to this question is actually quite simple. If we consider something on the surface of last scattering, when its light was emitted, it lay at a proper distance of only 40 million light years from us. However, because of the expansion of the universe, 13.8 billion years later, it now lies at a proper distance of 46 billion light years, even though the light has only travelled for 13.8 billion years. So just to sum up, the surface of last scattering is a spherical shell which is the greatest distance which light emitted by an object in the past can reach us. We can only see light from objects within the surface of last scattering. The particle horizon is slightly further away. So there are a few things such as neutrinos which pass straight through the early universe. If a neutrino was moving near the speed of light, we could see it if it was just outside the particle horizon. So that's region B in this diagram, whereas objects within the surface of last scattering are region A. And finally, we can't receive any information outside the particle horizon. That's region C in this diagram. Okay, now let's go on to the Hubble Sphere. As we've said before, the universe is expanding. If we plot the distance a galaxy appears to be moving away from us via its redshift against its distance, conventionally we use the unit megaparsec, which is 3.2 million light years, we get a graph which is roughly a straight line. This relationship v, recessional velocity, equals h0 times d is called Hubble's law, and h0 is the Hubble constant. It's equal to 68 kilometers per second per megaparsec roughly. So if we look again at Hubble's law and we put a value for d of 4.41 thousand megaparsecs, that's roughly 14.4 billion light years, then it predicts that the velocity a galaxy is moving away from us is the speed of light. So this distance when this happens is known as the Hubble radius. A galaxy lying at the Hubble radius should be moving away from us at the speed of light, meaning that its light could never reach us. However, things aren't quite that simple. The light from distant galaxies will take billions of years to us, and during this time the Hubble constant changes. The Hubble sphere forms a spherical surface 1 Hubble radius away from us. On the edge of the Hubble sphere, objects are now moving away from us at the speed of light, and if the Hubble constant didn't change over time, we could only view objects emitting light now lying within the Hubble sphere. Light from these objects would eventually reach us at some point in the future. So before we go any further, it's worth having a quick recap. The particle horizon, which lies at a distance of 46.5 billion light years from us, is the greatest proper distance from which information sent in the past can get to us. The surface of last scattering, which is slightly closer at 46 billion light years, is the current proper distance where the microwave background radiation we see today originated. We can only receive light from objects within the surface of last scattering. And finally, the Hubble radius is the distance which, from Hubble's law, an object is moving away from us at the speed of light. if the Hubble constant didn't change over time, it would be the distance at which light from an object emitted now could never reach us in the future. However, the Hubble parameter does change over time, but only very slowly. H of t is its value at a given time. H0, the Hubble constant, is its value at t0, which is the current age of the universe. So we need to consider something called the cosmic event horizon. This is the largest proper distance at which light emitted now will eventually reach us. The cosmic event horizon takes into account how the universe's expansion will change over time. If an object lies closer than the cosmic event horizon, then light emitted now will reach us at some point in the far future. If an object lies further away than the cosmic event horizon, then light emitted now can never reach us. Those of you who are less mathematically inclined can skip over this bit, but at a given age of the universe, which we call t, the distance to the event horizon is given by the following expression. In this, T max is the maximum age of the universe. This is infinity for the standard model of the universe. A of t is something called the cosmic scale factor, and it measures the size of the universe relative to its current size. If you want to find out more details about this, just have a look on my blog. And finally, c is the speed of light in a vacuum. Not all models of the universe have a cosmic event horizon. A universe in which the rate of expansion drops to zero was very popular before the late 1990s, although it's not widely accepted today. Such a model has an infinite event horizon. So what this means is that light from all objects, however distant, will eventually reach us given enough time. When we do the calculation for our current model of universe, that's the standard Big Bang model, then the answer comes out as 16 billion light years. So if we look at the picture, then any object within the Hubble sphere will be receding from us at less than the speed of light now. Objects which lie between the Hubble sphere and the cosmic event horizon are receding from us faster than the speed of light now, but eventually they will be receding from us at slightly slower than the speed of light, so eventually at some point in the far future the light will reach us. Objects outside the event horizon, we can never receive any information from these regions. Light from these objects will never be able to reach us in the future. So this diagram shows how the event horizon changes over time in the current model of the universe. As you can see, it increases very rapidly since the Big Bang, and currently it's about 16 billion light years. Now in the future it's going to increase much more slowly, and it will eventually level off at just under 18 billion light years, which will remain at that figure then for the duration of the universe. So have a look at this diagram here. It shows the event horizon in yellow, the yellow ring. Everything inside the event horizon, its light will be able to get to us at some point in the far future. Our local group of galaxies is marked with the blue oval, and the other ovals are other groups of galaxies. Now let's imagine 100 billion years in the future. Then the observable universe would look like this. All the galaxies have moved out of the event horizon, which has remained the same at 17.8 billion light years away from us. So the observable universe, that's light emitted by galaxies now, is only our local group of galaxies. That's all we can see.